All right. Good morning, everyone. Let's start. Do you have any questions? Okay. So last time, we were still somewhere in 11.2 confidence interval for population mean. The context is still that we have an IID sample. But now we assume that they're both unknown. And we want to construct, right, a 1 minus alpha confidence interval for mu. And we did give the answer in this case, which is x bar plus or minus t n minus 1 alpha over 2 s over root n. But we did not, well, we also kind of, right, started introducing the answer, the questions of what and why, right? So what is Tn, right? And the answer is a Tn, a T distribution with n degrees of freedom, is going to be a standard normal, the ratio of a standard normal divided by this, kind of like a normalized chi-square, right? You take the chi-square with n degrees of freedom, and you normalize it with n, right? And then take the square root, where we also require that the standard normal and the chi-square are independent. Now, about why, right? Why? So here, actually, this, right, this confidence interval comes from, so the confidence interval, right? You should always remember the confidence interval, this confidence interval, right? Not any other one. This confidence interval comes from the pivot random variable, that is x bar minus mu divided by s over root n. Okay. So basically saying, right, or constructing this 1 minus alpha confidence interval is the same as saying that the distribution of this pivot random variable is a Tn minus 1, right? So the confidence interval structure is equivalent to saying that x bar minus mu divided by s over root n has a Tn minus 1 distribution. And that's where we want to say why, okay? Why obviously means that, well, here's the working definition of the T distribution with n degrees of freedom. Here's our, pivot random variable, right? Why is why, right? Why, according to this definition, that this should have a T distribution with n degrees of freedom. And I kind of try to point out, right, that it's not exactly immediate from a superficial glance at the structure. Because, for example, if you just kind of look at the n here and the n here, you might think that, well, it should be Tn. But that's obviously superficial, right? Because the x bar minus mu does not have a standard normal distribution either. So the right way to look at, right, the connection between this and this is via, right, a cancellation that's hidden away from us. In other words, this right here will be equal to this right here divided by sigma square n minus 1 s square over sigma square, and then this whole thing divided by n minus 1 square root. Okay, so the the biggest cancellation, of course, I mean, there's several cancellation going on here. The trivial cancellation, right, of n minus 1, n minus 1, that's trivial. But the big deal cancellation, right? Why do I say big deal? Big deal because we cancel away the sigma, right? It's a big deal cancellation because exactly, right, this cancellation of a sigma allows us to operate with the context that sigma is unknown, okay? And you will see that later on, a lot of a lot of pivot random variable or a lot of test statistic operates this way. That is, they are structured so that somehow, right, the ratio, for example, involves the unknown parameter implicitly, right, like this. But because of the ratio, right, the unknown parameter got canceled, so that we can deduce the distribution that also is independent of the unknown parameter. Okay, so indeed, right, this will have the standard normal on top and square root of chi square n minus 1 divided by n minus 1 at the bottom, right, from our previous knowledge. And that's how we got, right? Again, right, I cannot emphasize this enough. It's trivial. I get it, right, from the algebraic point of view, but without this normalization, you cannot put this into a standard normal. Without this normalization, right, you cannot put that into a chi-square. But of course, the two mini, right, normalization you need on top and bottom are okay because they exactly balance each other out in the big ratio. Any question on this? Okay, so that's the why. Now today, right? I mean, if we want to be superficial about it and we would want to stay at the symbolic level, then this is all you need to know about, you know, a confidence interval constructed with T, right? That this is it, this is a definition, this is a structure. Most of the time, that's what you operate with. But you know, this is not this is superficial still from some other point of view. In other words, I think, right, your knowledge is incomplete without knowing a little bit more in detail what this T distribution is about. Okay, because right, that's just like the probabilistic background that helps you to understand the more subtle operation when, you know, things change. So in other words, right, we want to know more properties of the T distribution. Okay, and let me tell you, right, that there are certain properties that are well known, for example, but if I were to ask why, I think I'm just gonna guess that most of you cannot answer. For example, I think one of the properties well known is that if n goes to infinity, right, if sample size gets large, or even the degrees of freedom gets large, then the T distribution will converge in some way to the standard normal. Okay. In other words, right, the T confidence interval here, I'm sure, right, those of you who have taken any kind of elementary stat might have been told that, like, for n, you know, bigger than or equal to 30, then you can use the Z table instead of a T table, right, if you ever use the table at all. But that kind of statement, why? Okay, why is this statement true, for example? Another one would be the fat tail, right? The fat tail property. Right, of the T distribution. In other words, well, so first of all, right, I would argue that there are certain things that you can guess intuitively just looking at this structure. For example, right, and this may be easier, maybe not, but this is at some level, right, a standard normal divided by a positive constant. Okay, so at some level, it's like a rescale of the standard normal. But that's kind of putting it too, too simply, because this is a random rescale, right? The rescaling factor is independent of normal. That helps, but it's not a constant rescale, because if it's a constant rescale, then this will still be a normal random variable, right? It's a random rescale, well, whatever that means. But at the heart of it, because it's basically a rescale of the normal, it probably would not surprise many of us that the shape of the t distribution is still some kind of bell shape. Okay, so a t distribution still looks like this. All right, but of course you would ask, well, so what's the difference between this and a normal? Because seems like you insist, right, that is not a normal, right? So basically, maybe the first thing we should put is t distribution, right, is not normal. By the way, here I'm being lazy. I should say Tn, right? I should never say T alone, because that doesn't completely describe the distribution, right? So a T distribution is not a normal distribution, period, right? But the shape of it looks like a normal, right? A bell shape. So what's the difference? The difference, right, is exactly the fat tail. I mean, if you kind of want to be just intuitive about it, but what does fat tail mean? Well, fat tail means that if you were to superimpose, right, the graph of a standard normal and a t distribution, right, then this will happen. So the t, right, I'm not sure if I should. So the t is the outside one, of obviously the one above, and the one below, right, is the standard normal. Okay, so that right, that's what we mean by fat tail, right? The tail is fatter than the normal, right? Fatter compared to normal. All right, of course, right? Then the question is why, right? Why so? And I bring this up, right, because actually I claim, oh, by the way, that it's interesting that if you know enough, or if you're perceptive enough, then this actually is embedded in this definition. This property that as n goes to infinity, the Tn converges to z, all right, is embedded in this definition. On the other hand, I claim that the fat tail is not, I don't think it's possible to see in this definition, okay? But anyway, right, we kind of embed both of these in the properties, meaning we want to know more, not just construction and then just leave it at a symbolic level. Well, let me tell you, right, what's the consequence of a fat tail property of Tn? Well, the consequence of fat tail property of Tn is this, right? Let's just compare side by side. And this, by the way, is shown in the simulation, right? The Python simulation I showed you last time, which is on Canvas. That if you compare, right, the z, let's call it the z confidence interval for mu, which would be something like this: x bar plus minus, right, z alpha over 2 sigma over root n, and the t confidence interval for mu, which is x bar plus minus t n minus 1 alpha over 2 s over root n, right? So we did mention that this is unrealistic because, you know, population parameters are usually unknown together, right? There's no reason why you can somehow know the true variance of a population, you know, by a miracle. So anyway, so kind of like a bridge, right, between these two, and kind of like a mistake in some way, depends on the situation, is that you use a hybrid. You were to use x bar plus minus z alpha over 2 s over root n, okay? In other words, what are you doing here, right? Like kind of like a hybrid. And let me say mistake, not really, okay? And we'll discuss this. But basically, that, right? What you're claiming here is you don't know the sigma, right? So you replace it with S. But let's say that you're absent-minded, okay? You're absent-minded. You don't remember that you should use the T. You should use the Z. You just use the Z, right? Which happens a lot. Okay, what's the consequence? First of all, let's compare this side by side. All right, and it has the same center, right? It has the same kind of, unit. So the only thing that is different is the step size, right? Which one is bigger, the T1 or the Z1, and why? Between these two, right, which one is bigger and why? Anyone knows? Right, so yes, right, this one is bigger. This one is bigger in size, right? So this one is wider. So this one compared, right? So compared to this, the above one is wider. But that's correct. But now, besides the fact that you just kind of look up the numbers, right? Do you see, you say because of fat tail, I'm not sure you understand the reasoning behind it, or you just guess, right? Fat tail implies that. Do you see that exactly fat tail implies that this number should be bigger than this number? Well, the reason is this, right? And that's actually is true. The reason is this. Fat tails means that another way, right, is that the Z curve comes down, right, faster than the T curve. The T curve decays slower, more slowly. What that means, right, is that because both of these curves, the total area under a curve must both be 1 because they're both densities. But because the Z comes down faster, that means that it captures areas more quickly than the T. Agree? That means that, right, if I want to cover, let's say 0. I don't know, like from here to here, right, is, of course, the half of it is 0.5. So suppose I want to cover 0.4, then I only have to go out less compared to T, right? If I want to cover both probability of 0.4, then the Z, right, will have to go out less. So for that reason, right, Z alpha over 2 means, right, the area to the right is alpha over 2, let's say 0.05. That means to the left, right, the left half is 0.45. But because the Z comes down faster, right, that means I only have to come out less to cover the 0.45% probability, for example. Does that make sense? So, right, Tn minus 1, and this compares this way. Is that okay? Question? What this means, right, is that if you mistakenly, right, that's why I say mistake in quote, if you mistakenly use a Z instead of a T, it will or it might result in undercoverage. All right, it might result in undercoverage. Why? Because, right, you have to go out wider to properly cover 95% of the time. If you use less, you will cover maybe 92, 93, not 95. All right. So that was, one of the thing that one of the simulation result that I showed you last time. Now I put mistake in quote. The reason is, right, this mistake has a severe kind of degree, right, severity degree. In other words, actually, because of exactly this result, if your n is large, then this mistake is really minor and maybe you won't even see it, right? If so, this mistake the smaller the n, the more pronounced this mistake is. Okay, the smaller the n, the more pronounced this mistake is. But if n is large, then actually this is no longer a mistake. Actually, it's going to be a favorite approximation technique. In fact, I should not call it a mistake. It's going to be a confidence interval, right? But it's called a approximate confidence interval, right? So this is again another subtlety of statistics that you must appreciate in order to operate in this area. In other words, right, if n is small, this is going to be definitely a mistake. Because it will result in undercoverage. But if n is large, how large? Conventional wisdom says 30, but I'm not a big believer in that number 30, as you see. But anyway, right, let's just pick 30 for whatever reason. Then, right, these two are still will be more close. But still, right, at any point, this will be bigger than this. So, right, but of course, right, I mean, calculating like a t 59, right, percentile is tiresome. So why not just use a z approximation? It's more convenient in terms of calculation speed. All right, but because like the error you commit will not be too big. But for n, like if you have a very small sample size, like you only can collect 5 or 6 patients or something, then you definitely do not want to use a z when it's unwarranted. Any question? All right, so anyway, right, these kind of questions, like I said, the reason why I bring it up is because these are all covered under the properties of t distribution. And at some point, we need to be able to know, right, the density of the t to say this kind of to address this kind of question. In fact, right, exactly the fat tail right here requires us to need to know the exact density of Tn. I mean, exact is too much, but at least what the density looks like. For you to be able to say that, right, to say that the Tn has fat tail means that the density, right, comes down more slowly than the z distribution. Well, unless you know what the density of the T is, you will not be able to establish this rigorously. Okay. On the other hand, I claim that this can be known just from the working definition that we just posed. In other words, right, our working definition says that Tn is a standard normal divided by square root of chi-square n over n. I claim that this is enough for those who are perceptive to see that the Tn must be approximately normal or converge to a standard normal as n goes to infinity. Anyone see why? That this implies this. Wrong. Almost, but wrong. Because if you were to say that chi-square approach normal, which is true, yes, I know where that comes from, then you're asserting this is a ratio of two normals. Also wrong. Exactly, the last one is right. So, right, all of you got the intuition, but you did not get precisely, right? What Alice said is wrong because normal divided by normal is not normal, right? I mean, who told you that normal over normal is normal to begin with? So that's wrong. Christine is wrong because normal divided by 0 is not normal, right? Normal divided by 0 is infinity. And Samuel is right because n over n is 1, right? N over n is 1. So you all kind of pin it on the right factor, except that, right, precisely, right, what Samuel said is correct. In other words, what are we quoting, right? And this is where Alice, right, quote the wrong result. Alice was trying to quote the central limit theorem. Actually, this is a law of large number because the scaling factor is n rather than root n, right? So chi-square n, right, is by the working definition, is the sum, right, of IID, standard normal. And so, right, the ratio will exactly be, sorry, log large number. Okay. So what we're saying is that this right here, this ratio right here will be closer and closer to number 1 as n goes to infinity. Then, well, when you have a standard normal divided by 1, well, clearly you have a standard normal. Okay, so that is the reason. Question. So I still want to put, well, you know, some big name on this. Has nothing to do with this class really. But for those of you who are more mathematically minded, there is still some justification going on here, because even if n is large, at any level, this is still random over random. So a result called Slutsky's theorem will allow you to conclude that this is, you know, indeed is true. It converges to a normal distribution as n goes to infinity, but that's beyond our class. I just want to put it there as a, you know, a rigorous theorem that you will see that is used to justify it. At the level of our class, I'll be just very happy for you to recognize that this is 1. So that's that. Okay. All right. But anyway, right, this is true. In other words, for n large, if you look at the t curve, it looks more and more normal. Okay. So fat tail, right? Fat tail means we need to know the exact density of the Tn. So that brings us back to section 8 point something, which we skipped last time, where they discussed the T distribution. Eight 8.5. Okay. And there we pick up the density of the Z. In other words, well, so we are seriously in the probability mode where, right, we let X be something like, you know, do I want X here? That's fine, right? U over V, right? Where, right, U is standard normal and V, right, is square root of chi-square n over n. And we want to find the, you know what, actually no, right? I should do this. U over, and why do I do this? Let me just do this, Z over Y over N. Let's do this. Where Z is standard normal. And you know what, I apologize again too many times. I want to do this. This notation I think is a little bit more convenient. Y, X like this, okay? So X is gonna be chi-square n over, just chi-square n. All right. And so now I want to find the density of Y. That's what I'm looking at, right? The density of Y. And so where do we start? Well, clearly we start with something like, oh, by the way, maybe let me ask you, right? Suppose this is a probability question. What technique would you use, or how would you approach this kind of question? Well, I mean, it's going to be a calculus question that involves calculation anyway, right? There's no easy way out of this. But what technique would you use, you know, to kind of sit down and crank it out to find the density here? Mm-hmm. So what you mean is, I would need to do this. Okay. Transformation is actually a great idea, right? Transformation is a great idea. But, right, so transformation, would require you to come up with another pair, right? Another auxiliary, right? Random variable here, right? That actually is perfectly viable. That is good. But transformation, right, requires you to do another one, right? And use the 2 by 2 thing and then integrate out to get to the marginal, okay? I think just from experience, the transformation technique is slower here, okay? There are rooms, there are places where transformation technique is faster, as you see in the quiz. But here, I think the CDF approach is quicker, just because, you know, from experience, nothing else. So, right, but if I were to carry this out, that would be exactly probability of z over, right, square root of x over n less than equal to y. How do I proceed? Suppose I stay with the CDF technique here. How do I proceed? Well, one way you can proceed, right, is to right here use the joint density of x and chi square, right, or z and chi and x, because z and x are independent. Their joint density is just the product of individual densities, and so you would end up calculating a double integral, right, a double integral. So the technique I want to propose here is similar, except that it's going to be a conditional technique. All right, it's slightly new, but I think you should see it. It is used a lot in probability calculation. So what I'll do is this. I will do this. This is not surprising, right? I just bring this over, and because this is non-negative, it preserves the inequality. Next, what I'll do is I'm gonna condition on x. And I will integrate over all density of x. Okay, so this equality, right, is called the conditional approach. Not a point for this class, meaning I won't ask you to be responsible for such technique. But I want to show you because if you were to take something like stochastic processes 478, and if I were the one to teach it, you will see me using this like every single day or something like that. Conditional expectation is a big deal in some sub area of stochastic processes, okay, or even statistics here. Conditional expectation is very popular. What I'm quoting is something like at the heart of it. What I'm quoting is this so-called definition, this so-called property. Expectation of x is expectation of x given y, like this. So this is a law of, I don't know, repeating expectation or something. I don't know what the name of this is, but it's just basically expectation of conditional expectation gives you expectation. So when you want to calculate some kind of expectation or probability, you can condition and then integrate out. Yeah, thank you. I think that's more like it. The tower, right? Tower property. Thank you. I think that's more like it. Okay, but anyway, right? I just want to bring it out to tell you that this is not a strange thing or something. It's a very popular technique, and trust me, right? That this works. Anyway, all right. So what do we do from here, right? conditioning gives you several things. What it gives you is that here, right, because you condition on this equal to a value, you can replace this random variable with a single x. What that gives you is that allows you, right, to be able to replace this big X with a small x. But more importantly, because X and Z are independent, conditioning on Z conditional on X after you replace this with little x is without conditioning. It's like no conditioning because Z and X are independent. So what that means is this will split in for me like this. All right, like that. Where of course, again, right, this is the density of a chi-square. This is the CDF of the standard normal. So what I'm saying is the CDF of the t distribution is like the integral of the CDF of a standard normal times a chi-square density and integrate out. Any question? Okay. So let's see. Now, obviously, we do not know the CDF of a standard normal, right? Because the CDF of a standard normal requires you to integrate its PDF, and its PDF involve the term e to minus x squared over 2, which does not have antiderivative. So at this step, we're kind of stuck. We're kind of stuck a little bit. But never mind, right? We're stuck, but that doesn't matter because our ultimate goal is not to get to the CDF of the Z distribution, of the T distribution. We want to get to a PDF. So, right, how do we go from the CDF level to the PDF level? Right? What operator will carry us from here to here? Exactly, right? Differentiation with respect to y. So in other words, we will take this, well, ugly, it's not that ugly, right? This expression and differentiate with respect to y. So in other words, the density of the t distribution will be derivative with respect to y of this. Okay, well, is that scary? Well, depends. Here's the integral with respect to x. You are differentiating with respect to y. Y is embedded in here. There is this almost like a miraculous property of derivative. I'm not sure I mentioned in this class. You can switch integration and differentiation under some condition. Like this. Okay. So basically, you can bring the differentiation inside. But what allows you to do this, right? Or what kind of like intuition behind this? The intuition actually is the intuition of the differentiation that you used to know before. So for example, if you integrate, if you differentiate a sum, right? This is the sum of the derivative. This everyone will agree, and this is indeed true. The integral at the heart of it is a sum, but except that the integral is a limit, meaning like it's a continuous sum. So in other words, you're switching the two limits here, right? You're switching the limit of the integral and the limit of the derivative. And sometimes that causes trouble. But here, right, it's perfectly fine. If some integration condition is holds. But anyway, right, bringing the derivative inside the integral is, oh, actually we did this, right, in the, what is it called? The Khmer Rao. I think I did this. That's why it sounds familiar. But yeah, I'm using the similar, exactly the same trick there, right? So I bring the derivative inside. So anyway, right? differentiating this, recognizing that this is the CDF of the standard normal, gives us the PDF of the standard normal, right, times this, because that's a chain rule, right? You pick up this term times this. Is that okay? All right. So we have gone as far as we could, not unfolding, all right, not unfolding what these guys are, okay? Because this is a chi-square and this is a standard normal. Now it's time to plug in, okay? It's time to plug in what the densities are to see what the structure is. We have gone as far as we can, right? To carry out this integral further, we need to plug in what the form of these are. So we will ignore the integrating constants for now. The density of a standard normal, right? Recall, the density of a standard normal is this. Okay. What about the density of a chi-square with n degrees of freedom? Does anyone remember what that is? I believe, right, it's going to be x to the, actually, I don't remember. Let me look it up. Let's see. So I'll ignore the constant for now. It's going to be x to the n minus 2 over 2 e to minus x over 2. Okay, that's the chi-square. The constant in front is some kind of gamma. We do not care for the constant because we just want to get at the structure of the t distribution. The constant comes later. Okay, we just want to get to the structure, the form of the t distribution. So now plugging this in, right? So this integral becomes the integral from 0 to infinity, right? A constant. I will count this as a constant too. I do not care for the constant. What I get is e to the minus y squared, right, over 2 times x over n, okay? I got x to the n minus 2 over 2 here, and then this is going to be square root of x. That's 1/2, right? So that will put it up to x to the n plus 1, right? Minus 2 over 2. Let me put it like this. E to the minus x over 2 dx. Is that okay? Now, so the last thing to do is to integrate out this structure. Let me ask you, right? We did this at some point, some calculation like this. So this is the chi-square density. Oh, sorry. First of all, this is the chi-square density of the n, right? T. This is the chi-square density. This is the density of chi-square n. How would we integrate this out smartly? In other words, how do we do this without kind of involving some painful integration? Do we recognize that this is some, you know, form that we can use without, right, doing the integration ourselves? What I mean is, like, do you recognize what this is? This is the density of a chi-square with n degrees of freedom. And the signature, right, is because it's n right here. So this is n plus 1. Exactly, because right, you pick up this square root here. So this is nothing. This block right here should be viewed as associated with chi-square with n plus 1 degrees of freedom, the density. Okay. Then, okay, if I view it like this, then how can I take care of this? What about this exponential term? How do I take care of this? So let's simplify this a little bit. Suppose I have some structure like this. What does that remind you of? Or does this calculation, right, signify anything? Exactly, right? This is exactly expectation of e to a tx, or the moment generic function of x evaluated at t. So this right here, because everything should match up, all right? That's why I ignore the constant, because everything should match up. This is nothing but the moment generic function of the chi-square distribution with n plus 1 degrees of freedom, evaluated at where? Evaluated at this. So in other words, right, the density of y, right, by the way, right, this is the density of y. The density of y should be some kind of constant times the moment generic function of a chi-square with n plus 1 degrees of freedom, evaluated at minus y squared over 2n. Okay. Now, moment of truth or recall, right? If we have a chi-square with n degrees of freedom, what is its moment generic function? Right. So this is where once upon a time we were kind of so big on moment generic function, right? What is the moment generic function of a chi-square with n degrees of freedom? Well, again, right, these are not something that I keep in mind, so you don't feel bad if you don't keep in mind. You look it up, and it will be something like this. All right. So that means that for our T density, right, our T density, or rather, right, now we can switch it back to the density of a T distribution with n degrees of freedom evaluated at T, that will be, right, 1 over 1 plus T squared over n raised to n plus 1 over 2 with some constant. And here, right, T goes from minus infinity to infinity. Any question? Okay. So this constant is ugly, all right? It involves some gamma stuff. Look up in the book. I do not care for it so much because it's just an integrating constant. The structure of the T distribution is right here. So, all right, that was the technical hard work, whatever, but the techniques here is worth remembering, all right? Because at some point, who knows, you have to pull out some calculation like this. But anyway, right, that's what we get. Okay, why did we do this? We did this, right, to show the fat tail property of the T distribution. Well, what does fat tail means? Fat tails means that we want to say that this is more, right? This is bigger than the standard normal. So compare with okay. So comparing these two graphs, is it clear that this graph decays more slowly than this graph? For any fixed n, is it clear that this graph decays more slowly than this graph? Yes, right? The answer is sure, because this is exponential decay, while this is like a polynomial decay, right? And actually, you see that the decaying speed gets better as n goes to infinity, right? The larger the n, the faster the decay of this. But, it's at any level, right? At any fixed n, it cannot be compared to a normal decay. All right. So that's why this t always has a fatter tail than the standard normal. All right. What else do I want to tell you? All right. Maybe one last fun question, right? What about the moment generating function of the t distribution? Okay. Right, because I mean, when we worked with other distribution before, right, we were kind of big on the moment gen function. Here we just had the density, right? What can we say about the moment gen function of the t distribution? So before we even answer that question, right, let's just look at what about the t distribution with 1 degree of freedom. If we have t distribution with 1 degree of freedom, right, it will look like this. Sorry, not square root, right? Because this is 1 plus 1 over 2 is. So I guess two questions, right? First of all, do you recognize this as a distribution you might have seen before in probability? There's a name for it. And second, because of that, you know what this C is. And also maybe three questions, right? One, another name for T1. Two, what is C? Three, okay, you know another name for it. So what is expectation? So this is kind of testing your probabilistic knowledge, right? Does anyone know any of these questions? Well, one called Cauchy distribution. And you should, or you might have learned Cauchy as some special distribution because it's given as a cautionary example for something. All right. But two, what is C? Well, you don't need to actually know that it's Cauchy to know what C is. When you integrate this, what is the inverse, or what's the antiderivative of 1 over 1 plus t squared? Does anyone know? Tan inverse. Tan inverse. Yeah. So what's tan inverse at infinity? What's tan inverse at infinity? It's pi over 2. So what is C? 1 over pi. Right? And that, you see why, this is why I don't care to write down C in general. Some weird gamma thing that we don't care so much, right? All right. 3. What's expectation of a Cauchy? By the way, I hope that you have heard of Cauchy distribution. It's not a popular distribution, but it's usually quoted, right, for certain reasons. So you should be aware of Cauchy a little bit. What's the expectation of Cauchy? Or, you know, again, right, let's not even rely on our knowledge. Let's just analyze it for ourselves. Something like this, right? What is it? So let me help you out, right? This is, what do I want to say here? This is odd, this is even, so the whole thing is odd. You integrate over a symmetric, interval, so the answer should be 0, right? The answer is no, it does not exist. Okay, it does not exist. This, by the way, is one of the reasons why when I was in your quiz in the median, right? I asked you to show that the expectation of the sample median of a normal distribution is 0. I said there's some convergence condition that we need to check. It's exactly something like this. Here it does not hold. In the normal it holds. The reason why the convergence condition here does not hold is because basically, what do I want to say here? If you were to take the antiderivative of this, right, by u sub, what you'll get is something like, if you were to do it, right, basically you get to something like natural log of 1 plus t squared, right, over 2, something like that. But you cannot do this because basically you get something like infinity minus infinity, and that's exactly a undetermined form. Okay, it does not exist. And I don't have to tell you, right? But for example, if you want to take the second moment, what should this be? This is infinity. All right. Does not exist because this is purely positive. And if you look at this, right, the integral does not decay as t goes to infinity because this ratio is 1. So the area keeps getting larger and larger. So it's just infinity. All right. So to recap, right, the Cauchy distribution is something that has no moment, even starting from the first moment, right, and the second moment is infinity. So the Cauchy distribution, or for our purpose here, right, the t distribution with 1 degree freedom, is usually quoted as a cautionary example that to show you that moment for a random variable does not have to exist. Okay. So why did I bring this up, right? We were asking the moment general function for a t distribution. So suppose you look it up on Wikipedia. Guess what this entry will be for the moment general function of a t distribution? Does not exist. Okay. So don't waste time looking for it. The reason is this: a random variable has a moment general function if and only if it has all the moments. Okay, it must have all the moments like 1, 2, up to whatever, infinity. There's no infinite moment, but you can go up all the way before it has a moment change function, or equivalent. All right. So the fact that you don't even have, like, let's say the first moment here tells you that there's no moment change function. Okay, there's nothing to generate. So in general, keep in mind this, and that has to do, right? Again, why this peculiar property? Can you see what is causing this at the heart of it? What is causing this? What's causing it at the heart of it is the fat tail, property of the T, right? It decays too slowly. So when you take the moment, right, and this is where people don't appreciate the normal enough. The normal decays so fast that any polynomial you throw into it, it will converge. It will kill that polynomial, right? The polynomial grows like x to the n, but z to the n. But because the exponential kills it at the end, it makes the proper convergence for you. This one decays too slowly. Of course, again, with n large, then you have hope, right, for some convergence. But so the idea is this, that the T, right, distribution with n degrees of freedom has only moments up to n minus 1. Okay, I think. So if you have T2, like T with the 2 degrees of freedom, then you can have the first moment, but you won't have the second moment. So if you have T10, right, for example, starting with T3 and stuff like that, you can start to define the variance. But for the higher moments, then if you go high enough, it will start to go to infinity like this, or does not exist. Okay. So the umbrella statement is that the T distribution does not have a moment change function in general. But if you want to be a little more specific, it can have some moments up to some level. And I think the level is the degree of freedom minus 1. Any question? Okay. So another fun detail, and this is not about our class, but about application of stats, right? Or so maybe our class 2. So it goes back to the fat tail, okay, property of the T. I think, is actually more popular than you think it is. Like, it's in the pop culture too in some way, or if you want to call it pop culture. There is I mean, if you are in the business world, you might have heard of this guy, Nicholas Taleb or something like that. He wrote a book called The Black Swan, where basically he talks about things that we think are rare event are not as rare as it is. So, market crash and things like that are more often than not, I think. And so basically, right, it's a popular book, for people to read. It's kind of like top Amazon chart, things like that. If you pay attention at the end of things, he kind of refers to a T distribution versus a Z distribution. All right, the fat tail behavior. And this actually is known in the business world too, in the sense that there is a concept called VAR, value at risk, that bank needs to compute every day for their reserve. All right, they need to keep like a reserve so that like 99%, 99.9%, they do not go, beyond the reserve. But right, exactly because of it's not really the Z, it's whatever distribution they're computing. But if the tail end of the risk, right, I think you might have heard the term of the tail risk. If the tail end of the risk they calculate, right, is fatter, or I mean, if the reality of the tail end of the risk is fatter than what they calculate, then they end up, right, not having enough reserve, right, than they should. So in other words, right, if this is what happens in reality, then they end up like under covering their risk. And that is a big deal, right, for the bank, for example. And of course, bank likes to do this because that requires them to store less money, right, less reserve. They can make more profit. but they will entail, right? They will not properly cover the risk, for example. So these things, like, same idea, same principle, you can see in many places, okay? Not just in a class like this. All right. Question. All right. So we're done with 11.2 now. Let's move on to 11.3. This is going to be confidence interval for difference in mu. Okay. Oh yeah. You caught me there. I was trying to kind of wave my hand over it, but here's the thing, right? What I mean is this. So the moment, right? The moment. So expectation of Tn raised to the k, right? Will be what? Will be the integral of, right, t to the k 1 over 1 plus t squared over n raised to the n plus 1 over 2. Right? So the question is dt. For what value of k does this converge? Is that okay? And so it boils down to this. It's a fight between this and this. Because you see, this grows at infinity and this decays at infinity, right? But if you have the growth as fast as a decay, you're dead, because you will never have proper decay, right? The whole rule of adding at infinity is that at the necessary condition is you must go to 0, like this. And even this is not enough because it goes to the log, right? So at the end of the day, it's something like this where you learn from Calc 2 that I'm not sure you appreciate or not. This sum is infinity, right? But this sum is finite. This is the the drawing line, right? So this is the P series, right? Where if P is, so it's a P series where if P bigger than 1, then it converges. But if P is less than or equal to 1, right, it is diverges. And that's exactly this right here as well, just told in the language of integral, right? So when you look at this, it boils down to comparing what? Comparing the value of, let me erase this, right? It boils down to comparing the value of k versus n plus 1, right? Because this over 2 here is neutralized by the t squared. So that's why, right? This k versus n plus 1. And what do we see? We see that, right, for it to converge, it must be at least, 2 gaps apart. Yes, because 1 gap apart does not work. So in other words, k, so what are we saying here, right? So n plus 1 minus k must be bigger than or equal to 2. Yes. So in other words, n minus k must be bigger than or equal to 1, or k is less than or equal to n minus 1. And that's why I say it can only have moments up to n minus 1. Does that make sense? That's a bit of analysis there for you, but k versus, meaning right? There's a k here, right? And there's an n+1 here, right? The fight is between k and n+1. And if you go with the p-series observation or go with this calculation, you see that, right? This is k, right? This is n+1. You see that even when k is n+1 minus 1, right? Then that doesn't work. Or k+1, right? When the gap is 1, it doesn't work. So here the gap must be at least 2. But if the gap is at least 2, then the relation between k and n is like this. Is that okay? Decay of both? No. All right. Is this? Let's be concrete. Suppose n equals to 5. Okay. So the density of T5 will be a constant 1 over 1 plus t squared over 5 cubed. Okay. Yeah, but I'm not sure what you mean when you say that decay on both are the same. The decay, this one does not decay. This one grows. All right, this one decays. What happens is the decay must be faster than the growth so that convergence happens. Right? So here, grow and decay are the same, cannot converge. Here, grow is faster than decay, but it's not fast enough. So that's why it's still not converge. So it must be fast enough. Yes, that's it. What value of k does this converge? And so the final answer, or I mean, this is because these are integers, so it works like this. But basically, that the grow decay, right, must be at least 2 above the grow. So all I'm saying is something like this, really, that the integral of t, right, 1 over t to the p. So here, p plus epsilon, right, dt. Epsilon here must be bigger than 2 for conversions. That's all I'm saying. Sure. Yeah. Yeah, it is a fascinating area of math, but unfortunately, that's analysis. It is not something that we need to be concerned with here. But yes, if you want to do statistics rigorously, something like this, you need to know. Yeah. All right. Cool. All right. We're good. So let's continue, right? 11.3, confidence interval for difference in means. So now we're into the context of 2 samples. Okay. And let's suppose that these 2 samples are both from normal. So you have x1 up to xn, x1, 1, I guess, x1 and 1. Okay. Their IID, normal with mean mu1, varying sigma 1 square. x2 up to x2 and 2, right? IID, normal mu2, sigma 2 square. Okay. So the context or the question is, right, find the 1 minus alpha, find A1 minus alpha, confidence interval for mu1 minus mu2. And as you see, right, as we change the assumption on whether we know this or we don't know this, the relation between these 2 samples, we get different kind of answers. All right. So this is like comparing two samples. So for now, let's assume that these two guys are independent, meaning the two samples are independent of each other. All right. So how does the story go? The story goes just the same way as we did before, right? We start with the estimator. Well, what should this be? This clearly is x bar 1 minus x bar 2, right? Is this a pivot random variable? The answer is exactly, right? Not yet. And not yet, right? Because it involves mu1 minus mu2, right? So not yet. Well, actually, right, let's try to see why the not yet is the case. Well, what is the distribution of this? What distribution does x bar 1 minus x bar 2 have? Meaning, right, normal. But you know, right, normal is not enough. Normal, what mean, what variance? And by the way, right, what Samuel said is not incorrect, but exactly, right, it's a difference of two normals. And how can we go back to a normal? So difference of two normals is normal because they are independent, right? But anyway, it's ultimately normal with what mean and what variance. Excellent, exactly, yes. So mu1 minus mu2 and sigma 1 square over n1 plus sigma 2 square over n2, right? And where does that come from? Oh, Madaf, right? You missed that. And Samuel missed the n1, n2, right? We don't necessarily assume that they have the same sample size, right? Sample sizes. So, right, where do they come from? This is the difference in the mean. This is the variance of the first one. This is the variance of the second one. And when you take the variance, right, of the sum, right, or whatever the difference, it's going to be a sum of the variance plus the covariance terms. But because they're independent, the covariance term is 0, right? So we end up with this. Is that okay? And the not yet, right, comes from the fact that this is there and this is there. So obviously, right, that we make the cheap, assumption here. Suppose sigma 1, sigma 2 known, right? This is crazy, but anyway. Then what will be our pivot random variable? How would we normalize this? I guess it takes too long to type in the screen, right? Because I hope everyone sees this. Right? Which obviously has a standard normal distribution. So in this case, right, then the confidence interval is x bar 1 minus x bar 2 plus minus z alpha over 2 square root of sigma 1 square over n1 plus sigma 2 square over n2. That's our confidence interval because of this. Question? Now, but obviously this is not right anywhere near realistic, right? So the case where we're interested in is when sigma 1, sigma 2 unknown. right? So give me one moment, right? And I'll just propose a question. If they're unknown, right? How would you think the proceeding would go? Would it be something like this? X bar 1 minus X bar 2 plus minus some kind of t alpha over 2 square root of s1 square over n1 plus s2 square over n2? If so, what is the degree of freedom and how? All right, so maybe in the interest of time, let me tell you that if you were to put the t in here, there will be this, n1 plus n2 minus 2. You lose 2 degrees of freedom for estimating x bar 1, x bar 2. But even if that, this is wrong, okay? This is not going to be right unless you assume that sigma 1 and sigma 2 are the same. But if that's the case, then that's not the estimator to begin with. You will use this pool estimator S in your midterm one. So anyway, right, the point being is we need some careful analysis of what the distribution should be when sigma 1, sigma 2 unknown. And it shows you that statistics cannot be just, brute force through with formulaic guess. All right, you need to be precise in your distribution calculation. All right, so maybe I'll stop here, okay? And we'll pick it up after the spring break. All right, thanks for attending, guys, the last day before spring break, and have a good and safe spring break. I'll see you. All right. If there's any question, I'll answer. You too. Yeah, have a good break. Thank you. No, but if you want to meet with me, feel free to send me an email. I'm available. But officially, I won't hold office hours next week for spring break. But if you want to meet with me, feel free to send me an email. Sure. You too.